This will be a storytelling video. You won't learn any practical steps for actually answering questions from it. For that, just skip ahead to the next video. What I want to do instead is tell you a big picture story so that you'll be in the right frame of mind and you understand what you're really doing when you do actually answer questions. You should watch it and let it wash over you and then go on to the next video for the practical nitty-gritty and then come back to this video and you'll appreciate it more with some hindsight. Here's a timely story. Coronavirus testing. What is a false positive? It's by the presenters of More or Less on BBC Radio 4, a wonderful programme which will really teach you what it means to be a data scientist. There's so much credulous reporting based on latest figures show this or that or the other, and barely any journalists understand what it means to evaluate claims made about data. On More or Less, they look into the data behind the stories and ask if it really says what the headlines say it says. It's been a fantastic resource throughout the COVID epidemic. This is a new story explaining what a false positive is. You've learnt about them already. You've very likely already come across Bayes' rule and used it in its canonical application to reason about medical diagnostic tests. These are the questions it answers. What is the probability you truly have COVID, given that a diagnostic test came back positive? And what's the probability you actually do have it if the test came back negative? The way to think about all the possible outcomes is by drawing up a table like this. There are 4 possible cases. You might have COVID and the test comes back positive, or you might not have COVID and the test still comes back positive, and so on. This is called the confusion matrix, and it's a very good name because I get confused every time I look at it. I can never keep straight in my head what words like sensitivity and false negative and specificity mean. Now, the only way I can understand what's going on is by writing out a proper probability model. Here's the probability model behind the confusion matrix idea. First, generate x, a Bernoulli random variable. Let x equal 1 mean I have COVID, and x equals 0 mean I don't have COVID. In other words, x is the indicator of whether or not I have COVID. Now, generate y, another Bernoulli random variable. Y will be the indicator of whether or not I test positive. The distribution of y depends on x. If x says I have COVID, then y is very likely to be 1, but it's not 100% certain because the test isn't perfect. And if x says I don't have COVID, then y is very likely to be 0, but again it's not 100% certain. These numbers, 0.94 and 0.01, describe how good the test is. Next, apply Bayes' rule to this probability model. What's the probability that x equals 1, i.e. that I have COVID, given that y equals 1, i.e. that I tested positive? This is exactly the first question we asked. For the second question, it's easy to write out the Bayes' rule formula too. Okay, so that's Bayes' rule for a very simple probability model with 2 binary random variables. I spelled it all out like this, writing out this probability model, even though you likely already know Bayes' rule, because next I want to look at continuous random variables, and this is where things get tricky. Here's an example. Here's a probability model we looked at earlier, MP expense claims. First, generate a discrete random variable k, either 0 or 1. Based on k, generate a continuous random variable y with a normal distribution whose parameters depend on k. This is called the Gaussian mixture model, and the idea of k is that it separates out the bulk of the claims from that funny little hump around 2.7. Now, let's ask, if a claim comes in of size y equals 2.1, does it belong to the k equals 0 class or the k equals 1 class? Let's just go ahead and write out Bayes' rule. The probability that the random variable big K takes value little k, where little k is either 0 or 1, given that big Y equals 2.1, is just this Bayes' rule formula. Now another example. I generate x uniformly in the range -1 to 1, then I generate y to have a normal distribution with mean x squared. This gives me samples in a smile like in the picture. If I'm told y equals 0.6, what can I infer about x? Again, let's just go ahead and write out Bayes' rule. So, what's the issue? Pause the video and see if you can spot what's wrong with these two equations. In the first example, y is a continuous random variable, so the probability that y takes any particular value is 0. So this equation is 0 divided by 0, which is not very helpful. The second example is even weirder. Look closely at the conditional probability here. Probability that y equals 0.6, given that big X equals little x. Here, x is a continuous random variable, so the event we're conditioning on has probability 0. So how do we even define conditional probability when we're conditioning on something that never happens? Sherlock Holmes said, "Whenever you exclude the impossible, whatever remains, no matter how improbable, must be the truth." Here, we're assuming the impossible. To be precise, it's impossible in the sense of having 0 probability, which is actually a technicality which makes everything work. Okay, this has been a very long-winded introduction to get you used to the idea that there's something tricky and interesting about Bayes' rule. You've learnt Bayes' rule already in an elementary probability course, but now we're going to take it apart and relearn it so we know what it really means. This is where we're heading to, a reformulated version of Bayes' rule for random variables. Just read it to yourself. First thing, I've written it all in likelihood notation. The first goal of this video is to get used to this sort of notation so that all the terms here become second nature for you. Next thing, we're going to dive deep into the meaning of these terms. A likelihood conditioned on an event that might have probability 0. We're going to interpret this conditional likelihood in a completely new way to what you learnt in elementary probability. To get going, I'm going to start with a simple probability model with discrete random variables. Discrete random variables are nice because nothing goes wrong with them, and everything that we might write down intuitively turns out to be correct. That's actually a double-edged sword, because if we only ever work with discrete random variables, we never think hard about what's really going on. So I'm going to work through an example with discrete random variables, but put it under the microscope so that what we do in the discrete world we can transpose to the continuous world. Here's the model that we'll look at. This code generates a random integer x, and then, based on the value of x, it generates another random integer y. Here I've plotted the joint probability mass function, or PMF, of the pair x, y, which we're calling the joint likelihood. For discrete random variables, the likelihood, PR subscript big X, big Y, open brackets little x, little y, is just the joint probability of the pair, the probability that big X equals little x and the random variable big Y takes value little y simultaneously. And I can plot this as a 2D histogram just by taking lots of XY samples and counting up the number of times that each pair appears. Or I can do it in maths. I can split apart the joint probability using the definition of conditional probability, and then just substitute in the probability mass function for x, which is uniform, and for y given x, which is binomial. Next, let's talk about marginal distributions. The marginal of y is just the distribution of y on its own. We can get this from the joint PMF by using the sum rule, also known as the law of total probability. The probability that big Y takes value little y is the sum over all the ways that this can happen, the sum over all x of the joint probability. In other words, you sum up a row of the joint likelihood plot and you get the marginal. Or you can do it with code. We drew the joint likelihood plot by generating lots of xy pairs and plotting a 2D histogram. We get the marginal of y by summing up each row of the joint likelihood plot, and this just means counting up the number of times that each y value appears. In other words, we're just taking our x, y samples, throwing away the x and counting the y's. Next, let's talk about conditionals. You know the definition of conditional probability. It's just the joint probability divided by the marginal probability. Here, if I want to know what's the probability that big X takes value little x, given that big Y takes value 3, then by definition of conditional probability, it's probably that x equals little x and y equals 3 divided by the probability that y equals 3, i.e. the likelihood of the pair x, 3 divided by the likelihood for y of having value 3. In terms of the picture, if we want to plot this conditional probability as a function of x, which I've done in the top picture, this equation just says take the whole of the y equals 3 row, scale it so it sums to 1, and the correct rescaling must be to divide by the marginal for y, because the marginal for y is the row sum. And this gives us the probability of any specific x value conditional on y equals 3. Okay, now let me swivel around and look at what we've just done from a completely different angle. What we've produced is a probability distribution. It's a set of probabilities which sum up to 1. So it's a legitimate random variable. It has everything we'd expect a random variable to have. It has a sample space and it can be described with code. The sample space is just the same as that for x, of course, because that's all it's possible to produce. And here's code that we could use in this case to sample from it. Remember, we generated this entire 2D histogram by generating lots of xy pairs and just plotting the counts. So if I want to get a representative samples from the y equals 3 row, I just throw away all my xy samples that don't lie on the y equals 3 row, and what I'm left with is samples of the conditional random variable. This sort of code works fine for the discrete case, where if we sample enough xy pairs, we're sure to hit y equals 3 eventually. But for the continuous case, we can't start with code like this. We just have to start directly with the likelihood function. So let's summarize. Given a pair of random variables x and y with a joint distribution, we can define a conditional random variable, and it's written x conditional on y equals y. Its likelihood is given by this formula, which simply says take a slice from the joint density and rescale it so it sums to 1. It's more natural to write the likelihood in a slightly different way, which we read as the likelihood for big X at little x conditional on big Y equals little y. But the way I wrote it first is logically more correct. Great. Now we're ready to transfer these ideas across to the continuous case. The big picture to remember is this. We start from the joint distribution plot, and once we have that, we define marginal random variables and conditional random variables by operations we perform on the plot. Here's some code to generate a pair of continuous random variables. In this code, x is uniform in the range -1 to +1, and y is a normal random variable centered around x squared. Any pair of random variables has a joint probability density function, i.e. a joint likelihood, and the joint PDF is related to cumulative probabilities by the usual sort of integral. The probability of any joint event involving x and y is just the integral of the likelihood function over all pairs little x, little y inside that event. To write out the joint likelihood for a probability model of this sort, where the code first generates x and then given x it generates y, the joint likelihood is just the product of an x likelihood and a y likelihood with the appropriate parameters substituted in. The marginal distributions are what we get by integrating across a line of the joint density plot. Here's the marginal of y, which we get by integrating over x, i.e. integrating across a horizontal line. Okay, so we've got the joint distribution, we've got marginal distributions. Next, to define the conditional random variable, we're going to do exactly the same as we did for discrete random variables. From the joint PDF plot, we can take a slice through it. Here I've taken the slice at y equals 0.6. We rescale it so that it integrates to 1, and this gives us a legitimate PDF. In other words, it gives us a random variable, the conditional random variable x conditional on big Y equals little y. What I want to reiterate here is that when we do maths with this funny expression, likelihood for x of little x given big Y equals little y, we're not just pushing symbols around, we're reasoning about a random variable and its distribution. Okay, now we've got all the groundwork laid, we're ready to state Bayes' rule for continuous random variables. Here's a joint density plot for a pair of random variables x and y. On the left, I've taken a horizontal slice and rescaled it by dividing by the marginal, and this defines for me the likelihood of a conditional random variable x conditional on y taking some value little y. On the right hand side, I've taken a vertical slice, and this gives me the conditional random variable y conditional on big X taking some value little x. I put these together and I end up with Bayes' rule. The horizontal slice gives me a formula for the conditional likelihood of x in terms of the joint density, and then the vertical slice gives me a formula for the conditional density of x in terms of the joint density. Now, Bayes' rule is a mathematical theorem about two ways of slicing the joint density. But it's a pretty useless theorem unless we can actually figure out the terms in the equation. Bayes' rule is useful when the question tells us the likelihood for x and the question also tells us the conditional likelihood for y. Then we can use Bayes' rule to obtain the conditional likelihood for x. So that's the setting where we see Bayes' rule used, where there's a piece of code that first generates x and then generates y using that x value. This video has been very wordy, and you may at this point have no clue how to actually use any of the results in practice. That's all I wanted to cover in this video, to give you enough of a sense of what's going on that you're not scared by the notation. In the next video, we'll go through some very concrete practical worked examples with Bayes' rule, and after that you should be confident using it yourself. But just before finishing, I want to wrap up with a small note. This is a subtle point for those of you who have been paying eagle-eyed attention and spotted something that I tried to brush under the rug. This is what we said earlier. For a pair of random variables, to work out the joint likelihood of the pair x, y, given this code, we can just multiply the likelihood for x by the conditional likelihood for y, given x. But then I explained that conditional likelihood is only defined via the joint likelihood by taking a slice and rescaling. So this looks like circular reasoning. How on earth can I use the conditional likelihood of y before I've even defined the joint likelihood? Here's the right way to understand it. First, this decomposition isn't fair. We're simply not allowed to write down conditional likelihoods until we have defined the joint likelihood. Let's just write out the formula we're proposing for the joint likelihood. Let's call it f of x times g of x semicolon y for the obvious functions f and g. If the joint likelihood has this form, it's easy to derive the conditional likelihood. The conditional likelihood for y is the joint likelihood of x, y divided by the marginal for x, which I've written here as an integral. The integral is over y, so I can pull out the constant f of x term, like this. And then the f of x cancels from top and bottom. And also, if we defined our g function right, then the integral of g is 1, So we're just left with the g function. So in other words, the right way to read this setup is, here is some code. I propose this formula in blue for the joint likelihood. Because of how I defined the formula, we can easily interpret the terms in it. The first term is the marginal likelihood for x, and the second term turns out to be the conditional likelihood for y. In other words, we're safe. It's not circular reasoning.